host, Professor Scott Velasco.
Okay, Velazcoraptors, let's see if we can prove this idea, series and parallel. In order to do so, I've got a couple devices here that I'm going to have to explain so that we can figure all of this out. The first, right here, is a multimeter. And a multimeter's job is to make electrical measurements. In this case, I have it set to measure impedance. It is reading in ohms. And then over here, on this side, I have what's called a breadboard. Now, a breadboard is a way for us to test electronic circuits without actually soldering anything into place. So you can imagine it's a hugely valuable device to us. And it's set up in the following way. If you look, each of these rows, 1 through 30, has 5 holes on this side and 5 holes on this side. Those are A through E and F through J. Holes A through E in row 1 are all connected. And holes A through E on row 2 are all connected. But holes A through E are not connected if you connect 1 to 2. You have to stay within row 1 for those holes to be connected. And holes A through E are not connected to holes F through J, even in row 1. But holes F through J are all connected on their own. You get what I'm saying here. So, in order to test this idea of resistance, we can take the leads of our multimeter here, and I can touch them together, and you will see that the resistance being measured is just about 0. Now, I'm going to take the electronic component known as a resistor. Its job is to impede the flow of electricity. And how does it do that? If you were to split this thing open, maybe we'll split one of these open in one of our videos soon. But basically, there are a couple ways that they can be made. Most often, like this, they're made with a solid core, and it's just a material, and the density of the material determines the amount of resistance that the electrons face to get from one lead, just meaning one side of the resistor, to the other. So the idea is the electrons flow through the resistor. They can actually flow in either direction, and we'll talk a lot about this as we go on. But as they hit that center piece, their path is impeded. So they are, it's a little squeeze, we can say. Okay, so here is the formula that you need to understand. If our resistors are connected in series, what that means is the output of one resistor is connected to the input of the other resistor. Now, truly, resistors are not polarized. They don't have a positive and a negative side. They can be oriented in either direction. But as the signal flows through, let's imagine for a second it is flowing from the left side of the resistor to the right side of the resistor. That would tell us that the output, the right side of resistor 1, is twisted around or linked in or soldered to the input, the left side of resistor 2, and so on and so forth. And if these resistors are connected in series like that, you simply add their resistance values to come up with total resistance. So if you have, let's just say you have 3 resistors that are 10 ohms each, then your total resistance would be 30 ohms. If you had 100 resistors that resist 1 ohm each, then your total resistance would be 100 ohms. Okay, so what we're going to do is we're going to place this particular resistor, and I happen to know the resistance of this, but we are going to place it between 2 rows here. So between hole A on row 1 and hole A on row 5. And now we will take our leads and we will measure the two sides of this resistor, and our multimeter should tell us that there we go, about 10 ohms. 10.1, 10.2, it's hovering around there, but about 10 ohms of resistance. And remember, we use the Greek omega to signify ohms. Ohms is the measurement of resistance. Now, I have a couple more of these 10 ohm resistors. You say, how do you know that those are 10 ohm resistors? Because there are so many. I mean, resistance, we can go up into the mega ohms and beyond. How do I know that this particular resistor is only 10 ohms? And if you look carefully, there are a series of bands, and those bands are of various colors. And the colors and order of those bands can be read to tell us what the resistance value of this is. And you're going to learn that order and those colors and how to figure that out. But for now, just take my word for it. These are 10 ohm resistors. I'm going to connect these two resistors together. I'm going to connect these two resistors together by placing one lead in the next hole on row 5, the same place that our first resistor ended. This next one will begin. Remember, A through E are all connected on each row. So now we have two resistors, and we would say those two resistors are in series. One end is connected to the other, so end to end they are connected. And just for fun, let's go ahead and take a third 10 ohm resistor and do the same thing. End to end, so this will go into hole A on row 11, which is where our last resistor ended here. And now we have three 10 ohm resistors in series. And let's make our measurement. Let's see what we've got. You see it slowing down about 30 ohms. Well, that is exactly what we would want. 30 ohms, because we have added the resistance of each resistor in series, and that is how we get our total resistance. On the other hand, if the inputs and outputs of the resistors, again, sort of using a misnomer there, a sort of a false terminology, we don't think of it, but as the signal flows, let's imagine again from the left side of the resistor to the right side of the resistor. If all of your resistors have their left terminal bound together and their right terminals bound together, in other words, if they're just, instead of going from end to end in series, if they are all sort of connected at the same 2 points, we would say that is in parallel. And in parallel, the math is only slightly trickier. That you would take the impedance, the resistance of the first resistor, 1 over the ohms, plus the same 1 over the ohms of the second resistor, and so on and so forth for all of the resistors you have bundled. And what that is going to give you for total resistance is 1 over the total resistance there. And we'll do an example. What if instead we put our resistors parallel? Well, first, how would we do that? Certainly you're thinking about this right now, and maybe you've come up with some conclusions. But let's give it a try. going to take all three of our 10 ohm resistors, and they will share the same two rows, row 1 and 5. Now they would be considered in parallel. Let's make our measurement here. What do you think we'll see? Just a little bit of math, but I use 10 as a good number. It's a nice easy number to do our math with, right? Let's take our measurement and see if we get what we expect. Yep, it showed up there for a second. It's bouncing around just a little bit, but it should settle down right about here. Yeah, 3.4 ohms. There you have it. That's because the resistors are now in parallel. All right, well, I hope you take a few things away from this. First, how to calculate resistance across resistors in series and in parallel, what those differences mean, and also how we use a multimeter to measure resistance, and how we use a breadboard to test our circuit. Hope you've enjoyed this. This is Scott Velasco fading out.
Velasco! It was a Tuesday afternoon. It was a Tuesday afternoon. He put his hand on the door.